We're in Unit 2, Day 15 Notes, Part 2. So we're dealing, this whole sheet is a graphical approach, and then we got a couple of analytical approaches after this. So picture below is the graph of f prime, f prime of x, so that is the derivative. So these are all these represent the slopes of the tangent line on f of x over the interval from -3 to +4. So number one, on what open interval is the graph of f of x increasing? So, and it gets difficult, but this is where these positive values right here are the derivative. That's where the slope of the original function, slope of the tangent line of the original function is positive. So therefore, that's where it's increasing. So f of x is increasing when the derivative is greater than 0, and that's the only time it's greater than 0, which occurs on the interval -3, negative. All right, number two, what open interval is the graph of f of x decreasing? Justify your answer. So here, this represents where the slope is negative, and that means it's decreasing on the original function. So f of x is decreasing when the derivative is less than 0 or negative, which occurs in the interval from -2 all the way up to +2, not including the +2, and then again from 2 to 4. Because remember, the original interval was from -3 to +4. It says open interval, so don't include that 4. And then why it's not at -2 and +2 kind of answers question 3. At what values of x do we have a horizontal tangent on the original function? Well, the horizontal tangent is going to occur at the zeros. So when the derivative is 0, then I have a horizontal tangent, and that's at -2 and +2. All right, taking a look at number 5. At what value of x does the graph of fx have a relative minimum? Well, minimum, and I skipped 4, but let's do minimum first. So minimum means it has to go from it's decreasing and then it increasing, so negative to positive, and there are no relative minimums on f of x. At x equals 2, the derivative is 0, but we go from negative to negative, and then we go uh, negative to 0 back to negative. Sorry about that. Let's go back up to number 4. So where's the relative maximum? That's when the derivative changes from positive to negative, so that occurs at -2. And let's look at that on the graph. So here we're positive, we go through 0, then we go to negative. These are slopes. So therefore, on the original function, it's going to be increasing, get to a horizontal tangent, decreasing. That's a maximum. Okay, down here, it's a negative slope. Negative, negative, negative goes to 0, but then it continues going to negative. So there's no relative maximum. Actually, no relative minimum. And the last question, number 6, what is the slope of the tangent line? The graph of f of x at x equals 0, justify your reasoning. Slope of the tangent line drawn to f of x at x equals 0 is f prime of 0 equals -2. So you just look at the value, and at that instant, that means the slope of the tangent line is -2. Now, later on, they're going to ask us about the slope of the normal line. Well, if we can find the slope of the tangent line, which we just did here, so the slope of the normal line at 0 is going to be the negative reciprocal here, because the normal line is perpendicular to the tangent line. So the slope of the normal line would be +1/2. Just remind me in class, we'll talk about some vertical tangents and vertical cusps and the differences. I was going to write it down, but we'll talk about it in class. All right, so there's 3 problems that we're going to look at analytically, and here's the directions for all of them. For each of the given functions, determine the interval or intervals on which f of x is increasing and or decreasing. Find all coordinates of the relative extrema, relative min, relative max. Unless otherwise noted, perform the analysis on all values from -infinity to +infinity, and then provide justification for your answers. Okay, so the definition of a critical number, values of x at which a function has a potential maximum or minimum. Where does that occur? When the derivative equals 0. So let's take the derivative, set it equal to 0, and now solve for x. So we find x equals plus or minus square root of 2. So those are our critical values. So let's write those down. and we're going to write them on a number line. It's kind of the same thing we did back in um, pre-calc. We did a sign change chart. So on our number line, we know it's going to be 0 at negative square root of 2. It's going to be 0 at positive square root of 2. So I need to pick some values, something that's less than negative square root of 2, something that's between negative square root of 2 and 2, positive 2, positive square root of 2, and then something that's greater than positive square root of 2. And we try to pick numbers that'll work out pretty easy for us mathematically. And we're going to substitute this back into the derivative. Okay, so I'm going to pick x equals negative 2, substitute it in to the derivative, we get positive 6. So that means the slope is positive everywhere, because those are only two critical values, everywhere to the left of negative square root of 2. So it's positive, then it goes to 0, and then I chose 0, and I find out that it's negative 6. So the derivative is always negative there. So hey, if it's going positive on the original function and then goes to 0 and then it goes to negative, that's going to be a maximum value. We'll talk about that in a second. And we'll write that up formally. And now it's negative here, goes to 0, and then I find out when I substitute in positive 2 that it's also going to be positive, so it'll be increasing there. So let's write that up. First thing we know is the original function f of x is increasing on the interval from negative infinity to negative square root of 2. Again, from square root of 2 to infinity. Why? Because the derivative is positive. The original function f of x is decreasing on the interval from negative square root of 2 to square root of 2 because the derivative is negative on those values. So the original function f of x has a relative max at x equals negative square root of 2 because the derivative changes from positive to negative. I can then find the exact value by substituting in let x be negative square root of 2 in the original function. Put in your calculator, get 6.657, and square root of 2 is negative 1.414. And again, reminder, we're trying to go to 3 decimal places all the time. And lastly, we find the function f of x has a relative minimum at x equals square root of 2 because the original function, the derivative of the original function changes from negative to positive. Substitute into the original function, we get negative 4.657. So the relative min is actually at 1.414, which is square root of 2 in decimal form, and the y value is negative 4.657. Again, this is helpful because it's starting to give us a lot of information about the original function without using a calculator to just graph it and find those points. Obviously, we checked it. So let's go on to the next one. Why don't you guys try the next two, and I'll write them up, and we'll take a look at them. Okay, first thing we do is take the derivative, set it equal to 0, solve for x. We find out, hey, there's 3 factors multiplied together to give you 0, so at least one of them must be equal to 0. Do our sign change chart. And again, there are 3 zeros, so we pick the intervals not on those zeros. And again, any value, if I pick negative 2, negative 3, negative 4, negative 5, all the way up to negative infinity, substitute any of those in, it's always going to be positive. Because again, I'm on this side of the 0, so it has to be the same. Otherwise, I would have had another 0 in there. So again, we go from positive to 0 to negative to 0, back to negative to 0 to positive. So I think drawing these little arrows in help us figure out whether we get a max or a min. So now, again, where's the original function increasing from negative infinity to negative 1, and then again from positive 1 to positive infinity, because the derivative is positive. Let's look at the next part. These are all the things we need to do. Original function is decreasing from negative 1 to 0, and again from 0 to 1, because that's where the derivative is less than 0. And now let's look at relative max and relative min. So hey, I have a relative max at x equals negative 1. Why? Because the derivative changes from positive to negative. And then I can find that relative max because I know it happens at negative 1. So I put that into the original function. Negative 1, we get 2. So the relative max is at negative 1, positive 2. And now the relative min is at x equals 1. How come? Because the derivative changes from negative to positive. So it's going down, and then it's going to go up. So at some point it hits that 0, and that's where the minimum is. And I put it into the original function, and I get negative 2. So the relative minimum occurs at positive 1, negative 2. All right, let's look at the last one. Okay, for number 3, first of all, they put a restriction. It's from 0 to 2 pi, obviously. sinusoidal function would go on and on forever. So see if we get 1, 2, 3, 4 answers. So take the derivative, set it equal to 0, solve, and we find that theta equals 2 pi over 3 and 4 pi over 3. So let's now put this on a sign change chart. So, hey, 2 pi over 3 is 0, 4 pi over 3 is 0. And just, that's 120 degrees, that's 240 degrees. So let's use 90, 180, and 270. Let's substitute into the derivative. We find out, hey, cosine of 90 ends up being 0, so that's positive. Cosine of 180 ends up being negative 1, so that's 2 times negative 1, so that becomes negative. And again, I think the little arrows help. And then 270, 0, 1 plus 0 is 1, so it's positive. Again, you go positive up to 0, that's negative. That's going to end up being our relative maximum, and then go down to 0 and back up to positive. That's going to be our relative minimum. Okay, so we'll have max over here, minimum over here. So let's write those up. So first off, let me go back to my chart here so you can see both. The original function is increasing on the interval from 0 to 2 pi over 3, and again from 4 pi over 3 to 2 pi. Why? Because the derivative is positive, and the original function is decreasing from 2 pi over 3 to 4 pi over 3 because the derivative is negative. And the last part's here. Um, the original function has a relative maximum at 2 pi over 3, which I talked about before, because the derivative changes from positive to negative. We want to find that value where the relative maximum occurs, so I substitute in x to the original function. Hey, know that sine of 2 pi over 3 is square root of 3 over 2. Cancel out those 2, so we get 2 pi over 3 plus square root of 3, so the relative max occurs at 2 pi over 3, and 2 pi over 3 plus square root of 3. That's the x-coordinate and the y-coordinate. Now let's look where the minimum occurs. Very similar, same process. You're going to start to see these analytical ones, the same process over and over again. So original function has a relative minimum at x equals 4 pi over 3. Why? Because the derivative changes from negative to positive. Substitute it in. So 4 pi over 3 plus 2 sine. 4 pi over 3. We get same things, square root of 3 over 2, but the sign in the third quadrant is negative. These two cancel out, so I get 4 pi over 3 minus square root of 3. So the minimum occurs at 4 pi over 3, comma, 4 pi over 3 minus square root of 3. So that's your x-coordinate, that's your y-coordinate. Okay, these are your day 15 notes. We can start the homework now. This is part 2.